All right, so there were two questions that came up. One was about this S thing. What was this S thing? And you know, my short answer is go ask your math teacher. My longer answer, and obviously I'm not going to go through all of the theory of the S operator, but it's the idea of a transform. If you can take something that's a little bit problematic and transform it into something that's a little bit easier to deal with, and then deal with it and then transform it back, you're better off. Now, can I prove to you that it works? No. That's where I'm saying go ask your math teacher. But this idea of the S transform is this. Here we have a differential equation. I'm going to transform it using the S operator. And doing that makes it look like this. S squared V, okay, because that's what the S operator is all about. The S squared means the second derivative of V with respect to t, plus 7V, SV, right, because this is the first derivative, and then plus 10V is equal to, and then on this side, it would just be SVS plus 6VS. Okay, remember, VS is our voltage source, and it could be a function of time. It probably is. So here's the equation using the S operator. So what we used the S operator for was when we had the two equations and the two variables I and V, those two state variables I and V. And then I used it basically just to make it a simpler equation, and then I used Cramer's rule to eliminate one of the variables. So that's my answer on what S is. If you need a better answer than that, then again, sorry, I'm just going to have to refer you to like people like Fred Teddy, who's one of the math teachers here. So this also brought up the question about Cramer's rule. Like, what was I doing there? So just real quickly, Cramer's rule is a way to use determinants to solve n simultaneous equations in n unknowns. And the idea, so you could have like x, y's, let me just show it for like 3 unknowns. So let's say you have equations like this. Okay, so 3 simultaneous equations and 3 unknowns. So, you know, sometimes the equations don't look quite like this. You know, you might have the x on the other side or whatever. But you can always make it look like this, where you line up your x terms, you line up your y terms, you line up your z terms, and then you put everything else on the other side. And then what Cramer said, which is beautiful, is that you can solve for any one of these unknowns by just, well, pick one that you want. I'll take y. Let's say I want to solve for y. And it's going to be the ratio of 2 determinants. The determinant in the denominator is just going to be the columns here. So it's 3, 1, 4, 4, minus 3, 5, 5, 10, minus 2. Okay, there's the determinant in the denominator. The determinant in the numerator, it's almost going to be the same determinant, but the difference is that you're going to replace the column of the variable that you're looking for, so that's this middle column here because I'm looking for y, with what you have on the other side. So this one is going to look like this. So there's your answer. Now, of course, you've still got some work to do because you've got to evaluate the determinant. Remember, a determinant, you know, there's a way to, I'm not going to go into all that, especially with a third order one, but you know how to evaluate third order determinants. So there's your answer. So that's Cramer's rule, and you need to know Cramer's rule because you don't just have numbers. Remember, we also had S's as the coefficients of our unknowns, and so you need Cramer's rule and not just any, you know, because there's other ways to solve n simultaneous equations in n unknowns, but Cramer's rule is the one that you need to know because that's what's going to allow you to do it when you have like a term like s as part of the coefficient. Okay, so here is our second order differential equation that we need to solve. So again, if you have a standard second order circuit that's like a parallel RLC or a series RLC, you don't have to do all that work we just did. You don't have to find it because there's a shorter path. But now that we did that work and we feel really good about ourselves that we know how to do it now, here it is. We've got our second order differential equation. Now we've got to solve it. Okay, well, what's the solution to any differential equation? There's a natural part of the solution and there's a transient part of the solution. I'm going to get the transient part of the solution first. So what that means is you take your differential equation and you set the forcing function equal to 0. Okay? And then what you do, transform it using the S operator, so I actually did that work already. Okay, this is 0 here. And solve for S. Okay, and notice that now we can divide by V. So we've really got just a quadratic equation here. S squared plus 7S plus 10 equals 0. So solve for S. So S equals, what is it, minus B plus or minus the square root of B squared minus 4 times A times C all over 2A. And because I can't do math in my head, I can, but not in front of the camera. We get roots. We get 2 roots. One is minus 2 and the other is minus 5. So those are the roots, and we see that they are negative and distinct. Okay, there's going to be 3 possibilities. The roots are either going to be distinct, they're a negative, or they're going to be equal to each other, or they're going to be imaginary. So depending on which case you have, that determines which form of the natural solution you have. So there's only 3 different forms of the natural solution. And what we have here is the form that is called the overdamped case. Yeah. So there's only 3 cases. So we have the overdamped case, which says that our solution, the natural part of our solution anyway, is equal to A1e to the minus 2t, because you take the first root, plus A2e to the minus 5t. There it is. That's our transient part. Now, if the numbers had been different and we'd got, both of the roots were minus 2, then that would have been the critically damped case. And there's a different formula for that. If you had an imaginary, because sometimes you'll get imaginary roots, right? If you get a negative sign under here. If you get imaginary roots, then there's yet another formula for the natural part of the solution. But we have the overdamped case where we have distinct roots, and so here it is. We're halfway there, right? Because the solution to a differential equation has 2 parts. The natural part and the forced part. We just found the natural part. Now you may say, well, wait a second. We've got 2 constants and we don't know what they are. And you're right. We do need to figure out what those constants are. But I'm going to not do that right this second. But when I do get around to doing it, how am I going to find the values of those 2 constants? Anybody know? I said it earlier. Remember, these are the arbitrary constants in the transient or natural part of the solution to a homogeneous equation. Those arbitrary constants are always determined by the boundary conditions. That's why, at some point, I'm going to have to go back to this original circuit, to when the switch was in this position here with, I think it was a 10-volt source here. I'm going to have to go back to this original circuit and find the current at t equals minus 0 or 0 minus, find the voltage at t equals 0 minus, and that gives me my initial conditions. So we're going to have to do that work in order to find these two constants. I don't feel like doing it right this second. I'm much more interested in finding the forced part of the solution. And then I'll put it together and use those initial conditions to find these two constants. So let me put this up here. Okay, so we have Vn is equal to a1 e to the minus 2t plus a2 e to the minus 5t. That's just, one part. That's only half of the solution. Right now we have to go back to the differential equation and get the forced part. So here's the original equation. Okay, I can't have this equals 0 anymore because I'm looking for the forced part of the solution. Okay, we'll cut.